Yes, Barad sir, we are ready to go.
Okay. Good afternoon, all the participants, and especially the students of Chemical Engineering Department of RNGPIT and NG Patel Polytechnic. Myself, Dr. J.M. Barad, welcomes you all to this year webinar series. Today we are starting with a speech on hybrid membrane bioreactor. We have a speaker with us from Australia. Uh, Previous year, we had a very good experience of running this online webinar series. So we are continuing that healthy practice this year also. Today's topic is domestic wastewater treatment employing a novel buffalo osmotic membrane bioreactor microfiltration hybrid system. Dear students, we are aware that the treatment of wastewater is a key issue for chemical engineers as well as environmental engineers. And the chemical engineer and environmental engineer fraternity are continuously trying to solve this problem and reducing the water scarcity as far as possible. So in this area, there exists a novel research of hybriding this membrane bioreactor, that is activated sludge, is combining with a microfiltration and nanofiltration. And another one is unlike the reverse osmosis, there's a forward osmosis technology. So, like you, I am also curious to know about this technology. And to deliver this thing, today we have with us a speaker from Sydney, Australia. I'm welcome Dr. Niren Pathak for this today's session. Before that, I would like to introduce him that Dr. Pathak has completed his PhD in 2018 in the field of domestic wastewater treatment employing a novel buffered osmotic membrane bioreactor microfiltration hybrid system. He received his degree from University of Technology, Sydney, School of Civil and Environmental Engineering, Ultimo, NSW. He has also received Australian Postgraduate Award, APA, and UTS Research Excellence Scholarship. Currently, he is associated with research support activity with School of Civil and Environmental Engineering, University of Technology, UTS, Sydney, Australia. He worked on Central Park, Sydney reverse osmosis pre-treatment optimization project. He assisted with the project was assisted with outer selective hollow fiber osmotic membrane bioreactor project. He successfully designed, fabricated, and operated osmotic membrane bioreactor for research work for nutrient and organic micropollutant removal based on continual literature review. He published papers in reputed journals including Bioresource Technology. He is having hands-on experience using TOC analyzer, ion chromatography, atomic absorption spectrophotometer, inductivity coupled plasma mass spectroscopy, microwave plasma atomic emission spectroscopy, UV analyzer, drying oven, furnace oven, ultrasonic bath, Merck spectrophotometer, Hex spectrophotometer, etc. He performed the routine analysis of physiochemical parameters such as pH, conductivity, ORP, DO, and ion caption, COD, BOD, MLSS, MLVSS, sludge, sample extraction, and analysis. Dr. Pathak took master's degree in chemical engineering from SVNIT Surat and bachelor degree from Gujarat University. He is having long experience in academics as assistant professor in Sarvajanik College of Engineering and Technology, Surat. Before that, he has also served NG Patel Polytechnic as a senior lecturer. He had been a colleague to me, Dr. Latesh sir, and Karthik sir also, and very good friends of us. During his academic career, he has taught almost all subjects of chemical engineering, and many of them he shared with me also. So, on a very friendly note, he is readily agreed to deliver this session despite of the time zone gap. He has customized his time according to our convenience. So without taking much time, I would like to hand over the session to Dr. Pathak. So welcome, Dr. Pathak. Now
Yeah.
session is over to you.
Yeah. Thank you, Dr. Jaideep Barad, and all the faculties of Degree Engineering College and Diploma College as well. Hi, everyone, all the students and any faculties or the person looking to this presentation. Um it is really my privilege to deliver the speech with you guys. Uh, is it visible, my presentation slide?
Uh,
Hello.
yeah, no, sir. Can you please share it again?
Okay. Okay. I am on the entire screen. Now
Okay,
it, I think.
okay, yeah, yes, sir. Now it's visible. It's you can full screen and
So,
continue.
so is it whole slide is visible? Is it correct?
Yes, sir. Exactly, whole slide is visible.
Okay. So again, hi
Perfect.
everyone. I'm going to commence with my presentation. Just a kind of a clarification is Dr. Jaideep Barad mentioned. That's correct that I work on the baffled osmotic membrane bioreactor microfiltration hybrid system for domestic wastewater. That is my actually thesis topic. But what I'm going to present today is just as I show the agenda. Mainly, I'm going to focus on the membrane bioreactors, and then in the end, I will briefly mention regarding the osmotic membrane bioreactor. Definitely, I'm not going to speak on the baffled osmotic membrane bioreactor. During the talk of the membrane bioreactor, I will mention certain aspect, and then you will come to know what why I'm not going to speak on the baffled osmotic membrane bioreactor. So, as I came to know, the majority of the like audience is the undergraduate students, and I briefly talked with Dr. Barad that mainly you are studying like pollution control and the safety is one of the subject, and another is the novel separation technique. So what I try to do here is having this background, those who have studied that subject, we try to little bit in more detail or kind of more matching with your syllabi, we try to discuss the things here. So, in brief, I will talk about water scarcity and the background, followed by the membrane separation processes. This would be definitely a part of your novel separation process, and I will take in detail all kind of the membranes, their configuration, their characteristic, and kind of the thing. In brief, I will go through the wastewater treatment technique because membrane bioreactor itself is a advanced wastewater treatment technique. That means if you are aware of the wastewater treatment basic things, then this is bit advanced thing. And then osmotic membrane bioreactor is a recently studied one, like from 2008 onwards people have taken more interest in studying the osmotic membrane bioreactor. But once you understand membrane bioreactor conceptually, osmotic membrane bioreactor is not that different. So yeah, this is all about my talk. Okay, as we know, this is the global water supply, and left hand figure says the total global water. So as we can see here, that 96.5% water is always in the under the ocean, in the ocean, and other saline source is 0.9. So we have left out only with 2.5% of the fresh water. Now these 2.5% fresh water, again we can see that glacier and the ICAP has 68.7%, groundwater is 30%. So surface water or the fresh water that is mainly flowing into the river is again very little, 1.2%. And out of that also there is some segregation. So this is basically showing what is the water distribution on the earth. Now, number of the death by risk factor, that is in the year 2017, and this is like some IHME report. So if you see this red highlighted part, so unsafe water source. So these many 1.2 2-3 million of the death took place because of the unsafe water source. So again, water is very important commodity, and if you have that unsafe water source, then what happens that you can see. And now these are some of the water related challenges. As if you can see that 785 million people remain without even a basic drinking water supply. Unsafe water is responsible for 1.2 million deaths every year. What I want to here emphasize is roughly 75% of all industrial water withdrawals are used for energy production. So we are in engineering and we better understand that um, what is the importance of this. And 80% of the wastewater that we are going to discuss today flows back into the ecosystem without being treated or reused. So that is another important thing. Whatever the water we consume, 80% of the water, that what we call as a wastewater, it goes back into the ecosystem without being treated or reused. So both the treatment is the issue, especially underdeveloped countries, and the reuse of the water. And why it is important? Because we have still water related challenges, that is the water scarcity and the quality deterioration. So first of all, we have a less amount of the water, and another is the quality of the water. And therefore we need to understand the efficient use of the water resources, and again water reuse practices. So far there was no concept like water reuse, but now people are start thinking, and many more countries start implementing the water reuse practices. Another thing is, as community awareness increases, they are demanding to improve the performance of existing treatment plant. That means if like Bardoli town or the municipality somewhere, they are discharging the sewage or what kind of the polluted water without any proper treatment, then public understands and they raise their voice. So that is also one of the things. And the use of the treat water need a special attention as a new water resource. That means that is mainly again the recycle and the reuse of the water, that after treatment we need to bring it back to the process. And then there are so many possible reuse options, that what we are going to talk today. So in short, we have a stricter effluent standard, especially when the it is a sewage, that is a domestic wastewater or the industrial wastewater. In Gujarat, there is a Gujarat Pollution Control Board. They have some stipulated limit that you can't discharge water without properly treat, and they have specified some standards, some parameters. So these are the stricter effluent standard, and that because of that effective and the efficient system to remove the pollutant both from the sewage and industrial wastewater is essential. So how to achieve this target now? So there are so many conventional techniques already happening, but there are some other promising techniques, and one of them is the membrane bioreactor. So that's what we are going to discuss today. And it is by using the membrane bioreactor we can reuse the water to reuse standard actually. And if you treat the wastewater with the membrane bioreactor, so you can use that kind of the water in the domestic purpose like a lawn, toilet flushing in the hotel, resort and houses, as well as for the milk, fruit juice, textile and sugar processing industry also have their kind of the prospect to reuse their particular wastewater. Okay. So now, how to remove the contaminant from the water? So if you see the left-hand side, there are some of the methods suggested. So if you have any polluted water, what are the techniques available? So normally we go for physical method like sedimentation, then screening and filtration, and underneath in highlight like green one, I put that is a membrane separation. Another chemical methods are there. I'm not going in more detail, but last one is a biological method. So we have a physical, chemical, and biological treatment techniques. And in biological treatment, we have a aerobic treatment and anaerobic treatment. Now, if you can see the membrane separation and the aerobic treatment, I have already ticket mark because the membrane bioreactor exploit the advantage of both the membrane separation technique and the aerobic biological treatment. Now on the right hand screen, you can see why membrane technology, why I have tick marked the membrane separation or membrane technology. So there are some of the advantage and some of the, in the red underneath, there are some of the downside of the membrane technology itself. So we shall discuss them one by one. So now, as I said, that there are some of the parameter. If you have a polluted water and if you want to discharge it to any of the water bodies, there are some guidelines that you have to treat water at certain standard, certain level. So depend on the local context. Local context means from which geographical area are you in and what kind of the environment you have, what kind of the discharge. Some people in certain area you have to discharge on the land, certain places you have to discharge on the river, on the ocean even. So that are your local context. Now mainly the bacteriological parameter, that means bacteria, virus or pathogen is there in the wastewater. So we have a E. coli and Giardia kind of the bacteria. Importantly, nutrients, you can see nitrogen and the phosphorus, suspended solid and the turbidity. For that kind of the removal, to get rid of those kind of the pollutant, we have either sand filtration or ozonation or membrane bioreactor or other biological treatment or the flocculation. So that's the reason we have selected the membrane bioreactor. Some other things are the dissolved salt, heavy metal, boron-like compounds, harmful organic substances. So for that, you have a MF, that is a microfiltration, you have ultrafiltration, plus combination of the reverse osmosis, that is one or more combination, then some other advanced technique like advanced oxidation process. So these are the normal used techniques for the pollutant removal. Now, as I spoke before, why membrane technology? So this is continuous work. You can operate membrane continuously. Combination, you can use the membrane with another technique, that what we call integrate the membrane with the other treatment technology like aerobic treatment or some other technique, that is combination, or we call is integrated or the hybrid technique. That what we are uh, talking about, like hybrid membrane bioreactor and osmotic membrane bioreactor. So this is combination. Low energy, so compare to the membrane distillation or other kind of the technique, sorry, only distillation and other kind of the technique where there is a very high energy consumption. Comparatively, membrane techniques are low energy consumption. And the upscaling is easy. You can easily make the desired pore size or the surface charge, and the scale up of the module is possible as per your requirement. For example, in the wastewater treatment, if there is a small town like 3,000 people equivalent, you can scale up the membrane module accordingly. If it is a very high capacity and already it is in practice, then you can design the thing accordingly. Another adjustable property, as I said, pore size and the hydrophilicity, hydrophobic kind of the characteristic, surface charge. And importantly, there is no additive. You have been studying mass transfer operation, and in certain technique like extraction or other technique, you have to add something from outside and then it has additional impurity in the final product. But membrane based separation, you need not to have any additive from the outside. That means it gives you the pure product. If you see the drawback, so fouling is one of the issue. We frequently discuss this word in this talk also. So one is the fouling, low lifetime. Low lifetime in comparatively as compared to, as I say, distillation or other operations. Membrane has a specific lifetime like 5 years, 7 years, 10 years. So you have to replace them after. And that is called permeability and the selectivity trade-off. So when I say permeability, that means the flux. If you have a membrane, how much water can pass through that and how much pure water you get is called permeability. Selectivity is the desired product. If you are only after the pure water, but whatever you do, you can't get only pure water like a distilled water, but there is some ions involved in there, and that is called selectivity. And selectivity changes. So permeability is one aspect, selectivity. Always there is a trade-off between the permeability and the selectivity. So you can't achieve pure 100% pure water. So that is one of the things. Now, already I started talking about the membrane, having assumed that you already have some background, but okay, technically, um, before starting the membrane bioreactor, we need to understand what is membrane. So if you consider kind of the filter at your home that you use for the tea separation, so you put the seeds and you boil with the water in the milk, put some sugar, and when the tea is ready, first thing you have to do is the separation using the kind of thing in your kitchen. So it has a small sieves, and the tea percolate down, and all the seed settles on that. That is exactly the membrane function. So if you have a mixed kind of the thing, maybe some suspended solid, some dissolved solid, and the water, there is a membrane. Membrane is nothing but the plastic sheet, and that plastic sheet has a very very small, very fine pores inside that. So it only allow, technically it only, if we try to fabricate the membrane in such a way, the pore size are such a small as possible, it only allow the water to pass through, and all the other impurity settles on the membrane. As again we try to understand with the same example in kitchen, that when you try to filter the tea, what happens after, in the beginning you have a very high flow rate of the tea coming through that device, but after some time, because all the seeds are settled on the top of that filter, as a result it offers some resistance and it makes a kind of a cake. Same thing happens in the membrane process. If you have a plastic sheet with a small pores, you allow the water to flow through. After some time, all the impurities start sitting on the surface of the membrane, and it makes a cake layer. That what we call membrane is fouled. With time it happens. Technical fouling is a bit different, we will discuss in more detail, but this is kind of understand concept. As a result, water flow rate also decreases with time. So initially you have a high flow rate. After this cake layers formation start, you have a low flow rate. So now if you read this, membrane is a physical barrier between two fluids. When I say fluid, mean gas, liquid. Here we are talking mainly of the liquid phase, but across the membrane. One is at one side of the membrane, other is the another side of the membrane. So it works as a physical barrier. Now, synthetic membrane is a interface that separates the two phases and restrict the transport of various chemical species in rather specific manner. That what we call selectivity. And the membrane can be thought of a material through which one type of the substance can pass more readily, that is water, than others, and thus presenting the basis of the separation process. And importantly, 90% of the membrane, that what we are going to discuss today as well, are made of the polymeric material, that is basically plastic material. Now that is the first time membrane, what I wrote in here on the top, you can see overview of the membrane bioreactor. So first part is a membrane, another part is the bioreactor. So bioreactor refers to any device or system that supports a biologically active environment. So when I say biologically active environment, means the bacteria or the microorganism. But this microorganism, whatever it is, but for our process, for our bioreactor, for membrane bioreactor, that are useful kind of the bacteria that we need to understand. Now, don't confuse with your chemical reactor, because I see in the novel separation technique, those who have studied or are studying, there is also reactors, chemical reactors, but that are entirely meant for the chemical reaction and to get the chemical products, including the membrane contactors. What we are going to talk today is entirely different thing. We are going to talk on the membrane bioreactor. So membrane is a one separate thing, bioreactor is another thing. As I mentioned, it biological thing happens in the bioreactors. And then when you combine the membrane and the bioreactor, what we get is called membrane bioreactor. So membrane filtration and activated sludge process combines, and then it is integrates hybrid that called membrane bioreactor. So as I said, integrating the biological degradation system of the waste product with the membrane filtration. So biological and the physical process, membrane is a physical separation and the biological reactor is a biological process. Now, membrane bioreactor actually combine conventional biological treatment process with the membrane filtration to provide an advanced level of organic and the suspended solid removal. So again, what we are going to discuss is the wastewater treatment. So conventional biological treatment is already there that treats the water, but this is kind of bit advanced technique what we are going to discuss. So already conventional biological treatment is there. We are going to use a membrane and that leads to the separation. So it is a state of art third generation treatment process. But now I say already membrane bioreactor is a mature technology. So there are so many plants around the world in many more countries that already are in operation. So it is like a mature technology where it is applicable. So as I say, municipal wastewater treatment. So municipal wastewater treatment is basically whatever the things go from our toilet in whatever the form, it is called municipal wastewater or the sewage. So it is sewage treatment plant. Another is an industrial wastewater treatment. So it can all kind of the industry, textile industry, pharmaceutical industry, whatever it is you take, petrochemical industry, all industry have something as a waste product, that is industrial wastewater treatment. Agricultural waste treatment. In agriculture also there is some waste because they use pesticide, insecticide, many more other fertilizer. So sometimes you need to treat that water as well. Pharmaceutical, food processing, landfill leachate, nitrate removal in the drinking water. You must have studied about the blueberry disease. So why nitrate removal is important. Solid waste digestion for the odor control, tannery, winery, and water recycling in the building. So these are the major application. I have two of them, industrial wastewater treatment, because I will show you one of the case study of the industrial wastewater treatment. Another is a water recycling in the building. I will just talk about it briefly. I'm not going to show any case study about that. Now, we are going to discuss in detail the membrane bioreactor, but what is the conventional activated sludge process? So biological wastewater treatment with the activated sludge process, that is the conventional, that is already in the operation, this kind of the technique. So if you take the example of India, Baradoli even. So in Baradoli or even Surat or any surrounding city, still we haven't implemented any membrane bioreactor. That means at present what we have is the activated sludge process. This is based off my knowledge. I'm not sure yet, but based off my knowledge, there is no membrane bioreactor. Okay, so this is our conventional activated sludge treatment. So how it works? So if you can see from the left hand side, it is influent. Then there is a bar rack, grid chamber, primary clarifier, then say aeration tank, secondary clarifier, disinfectant, and the final effluent. So in one line, I try to mention each of the operation. What happens when the wastewater comes? That is either sewage. When I say sewage is a domestic wastewater, comes from the toilet mainly, or an industrial wastewater. First is goes to the bar rack and see coheres solid, very big kind of the solid such as a stick, rags, and other debris. It get rid of here. Then comes the grid chamber. So grid, sand, gravel, that kind of the material. You can see grid has removed. Here there are screens. Now importantly, primary clarifier. So what happens in primary clarifier basin? Basically, it is a sedimentation process and you get rid of 50 to 70% of the suspended solids and 25 to 40% of the biochemical oxygen demand. So this is one of the parameter BOD and the COD that describes the biodegradable organic available in the water. So whatever sort of the water you take, when you use the biological treatment means it has some biodegradable fraction, some organic material. So when organic material reacts with the bacteria, that means bacteria eat up the organic as a food like us. We eat all the food that are organic in the nature and we digest. Similarly, bacteria eat up that food, they digest. And as the name says, aeration tank, after primary clarify, you have a aeration tank. So aeration tank means it requires some air, oxygen transfer. So in presence of oxygen only, bacteria can survive. Therefore, that is called aerobic process. Bacteria has that characteristic. They need oxygen for the survival. So they take up the organic food. They have oxygen present in the system. and as a result, they survive, they grow, they manipulate, population increases. So now basic difference, this is the primary. What I am talking is primary clarifier can remove 50 to 70% suspended solid, 25 to 40% of the BOD. That happens already in the primary clarifier. Now primary clarifier, you can see on the top is a sludge, is called primary sludge or the chemical sludge. Why? The reason is in primary clarifier, we input some chemicals. So this chemical, actually it is a coagulation and precipitation process, and it sediments. So first it forms the flock, that is a chemical flock, and some electrolyte kind of the material is there. So it combines all the small particle that is suspended on the water, and then it make a flock and it settle down. And after settling, you have a thick kind of the material, kind of solid material, what we term as a sludge, and that sludge is known as a primary or the chemical sludge. So in primary clarifier, this thing happen. And next step is the aeration tank. So what actually I discuss how BOD removal take place, that in the presence of bacteria. So influent of the aeration tank is mixed with the activated sludge, and in aeration tank the mixed liquor is aerated. Aerated means oxygen is supplied. You have to bubble the air actually using compressor. And by aerating the mixed liquor, the aerobic process will be stimulated. Growth rate of bacteria will be much faster because the bacteria deplete the substrate. Substrate means any food or the organic substance. Flocculation take place and the soluble substrate becomes solid biomass. So in primary clarifier or primary tank, we have a primary sludge or the chemical sludge. Next step is a aeration tank, and second next to that is the secondary clarifier. So what now we are talking is the secondary clarifier. In primary clarifier, primary sludge and chemicals are used. In the secondary or aeration tank, we have a bacteria, that is a live microorganism. They eat up the food, and after that you have the sludge, but that is called secondary sludge or the biomass because it comes from the bacteria. So as we know, bacteria has a life cycle and it is very short. So after some time, bacteria will die, and then all this settles in the secondary clarifier in the bottom. Of course, there is living and non-living, both kind of the species is there, but that is called solid biomass. So secondary clarifier is different from primary, is there is no chemical sludge, but that is the biological sludge. And if you see again from the secondary clarifier, return activated sludge. So whatever the solid sludge you get in the secondary clarifier, equal RAS, recycle or return activated sludge. 70% of the sludge recycle back to the aeration tank because we need bacteria to retain the system, to continue the system. So we continuously blow the air, we continuously keep the things in the contact with the bacteria. There is an organic, they eat up the things. As a result, they degrade. That is called biodegradation, degrade the material and make in small elements, and then that water is ready to discharge. And after that, last step is a disinfection. Disinfection is nothing, you blow, allow the chlorine to pass through the system. So if any pathogen that is harmful to a human being, we try to kill them, and then effluent is the final process thing. So if you say influent is something coming from your toilet or any industrial waste kind of the water. After all these steps, more or less same, little bit sometimes changes, they call advanced treatment, but at present we are not going to discuss that much. And effluent is the ready to discharge either into the river or any water bodies or onto the land if there is no water body available, or in the ocean even. And these effluent has some specific norms, some standards. Government doesn't allow to just discharge the water as you like. You have to have meet some standards. So here one parameter we have a BOD. So for this kind of the effluent standard for the BOD is 30 milligram per liter. You can't go beyond that. If it is COD, chemical oxygen demand, then it is 100 normally. Now this is more important, because I'm going to use some of the terminology when I will speak about membrane bioreactor. So this is kind of the stoichiometry bit, you can say. So activate sludge process. This is the aeration tank. There is a mixture inside. Next to there is a clarifier. You can see it is a conical shape. What happened? Influent flows into the aeration tank. It mixes, and here it's not shown, but oxygen continuously pass through that. So bacteria eat up the thing, and whatever the supernatant, that means from top, whatever come, it goes to the clarifier, and then it's settle as a sludge. So part of the sludge we totally waste. We totally waste mean we discharge, but one part they call return activated sludge, we bring it back to the aeration tank. So this aeration tank is a main piece of the equipment, and the bacteria is the heart of the process, or we can say it is a dark horse of the process. In presence of bacteria and the oxygen, biodegradation of the food or the organic matter take place. Now there is some stoichiometry. So flow rate, Q is the flow rate of the influent, S0 is called substrate. I have written everything. Influent soluble substrate, that is a BOD, and how it is expressed, gram per meter cube or milligram per liter, that could be the unit. X0, X0 is a concentration of the biomass in the influent. So how much biomass in the influent? This is in the reactor. How much organic thing in the reactor? XR is the concentration of biomass in the return line. This is XR, and V is the volume of the reactor. So we will play with two terminology. V is the volume of the reactor, and Q is the influent flow. That is more important to us here. And then wasted sludge, that is QW. Whatever the sludge you are going to waste is called QW. And the effluent, so you have a Q is the influent flow, minus you have wasted QW, so you left out is the amount of the effluent. Very simple, input equal to output. So you have a Q, you have wasted QW from the clarifier, you left out with the Q minus QW. So now using this term, we have to define some biological process parameter. So first important parameter I will frequently talk in membrane bioreactor is hydraulic retention time. Now you know the retention time. Any reactor have a retention time. So once the water enters into the reactor and it leaves from the reactor, that total time is called retention time. And hydraulic, it is kind of a liquid, so hydraulic retention time. And same thing if you want to express in mathematical way. So it is a ratio of the tank volume, as we know, volume of the tank, and divide by the flow rate. So that is there. Solid retention time. Second word is the solid retention time. So solid retention time is the biomass. Biomass are considered to be solid, bacteria. So how long these bacteria retain into the system is called solid retention time. Sometimes it is called sludge retention time. It is also known as a sludge age. So residence time of sludge in the reactor is called this. And now I am trying to compare here, because I am talking on membrane bioreactor. So for conventional treatment, that what this one, this is conventional treatment. I'm not talking of membrane bioreactor yet. In conventional treatment, sludge retention time is 5 to the 20 days. And for membrane bioreactor, it is normally 20 to 30 days. That means it is longer than the conventional treatment. Another is a food to the microorganism ratio. So how much organic, how much wastewater you are giving as a food, and how much amount of the bacteria you have in the system. You decide how much bacteria should retain in the system. So if you have given X amount of the food and you have a Y amount of the bacteria, so this ratio is called FM ratio, that is food to the microorganism ratio. That means if you have more amount of the microorganism, they can easily eat up the food. If you have a less amount of the microorganism, it takes little longer time. And they have some complication on the process, or some good thing on the process as well. So ratio of the substrate is the food, that is an organic matter, and it normally represent by BOD or the COD, to the biomass. Biomass is the bacteria. And if you want to calculate mathematically, so FM ratio is equal to S. S is the substrate, QW is the flow rate, V is the volume of the reactor you are going to divide, and X is the biomass. So all these things give you the FM ratio, and normally it is expressed in the day inverse. So if you calculate mathematically, you will left out with the unit is called day inverse. In SRT, you get the unit is the day. So it is very simple. It is mathematics, nothing more. So FM ratio for conventional treatment is 0.05 to 1.5 day inverse, but for the membrane bioreactor, it is less than 0.1 day inverse. So it is less in the membrane bioreactor. And I am talking of microorganism here. You have certain amount of food, but how much microorganism or bacteria you keep in the system? So MLSS is 2000 milligram per. Normally it is 3000 to 3500. This is very restricted value, I say. But still, you can say it is 3 to 3.5 gram per liter. That means 3000 to 3500 milligram per liter in conventional process. In the membrane bioreactor, you can keep this value up to 20,000 milligram per liter, much higher value. That means you can retain, you can keep very huge amount of the bacteria or the biomass for the same amount of the food. That means your process become faster actually. And how that simple? Because of the membrane, we will talk that. And last is the sludge yield. Yield, you understand the word. So ratio of the cell, that is a biological sludge formed to substrate consume. That means if you consume 1 gram of the food, how much amount of the cell growth has taken place? That what we call sludge yield. And now there is some comparison. You can see sludge production kilogram per kilogram BOD. That means how much amount of the biomass have grown. That means with age our weight also increases. So with time, how much weight of the biomass increases in the system? Initially it was 1 gram. For example, it is very tiny. We can't say even 1 gram, for example. So 1 gram. But if it eat up the 1 gram of the BOD, or 1 kilogram and 1 kilogram of BOD, how does it work? So if it is submerged membrane bioreactor, that our interest is, it is 0.3 maximum. But if you take the last second one, conventional activate sludge, that what I describe now, it is 0.6. So that is the difference. In conventional system, it is 0.6 kilogram per kilogram BOD is a sludge yield. In the membrane bioreactor, 0.3 is the maximum. So in membrane bioreactor, deliberately, we do not allow the bacteria to grow. And there is the reason. By either you do by inputting the more amount of the bacteria to the system, so food divides in between them and they can't grow that much. But there are some advantages of that as well, because if you have a less sludge, you have no sludge handling issue, because finally when you discharge the sludge, one is a water part, you are treating the water. Another, you are just converting your wastewater to the solid product because it is sludge, part of that, not all. But then you have to handle the sludge, and that is big issue. So in membrane bioreactor, if you produce a less amount of the sludge, it is benefit to you. Okay, so again I brief the same parameter in short. SRT, you can see FM ratio, it is again SRT is high and FM ratio is low, and MLSS is always high. Now we briefly talk about the energy consumption. So CAS, first one, is a conventional activated sludge process, or we call ASP, activated sludge process. So energy consumption is 0.15 kilowatt hour per meter cube. So if you treat 1000 liter of the water, you have to consume 0.15 kilowatt hour of the energy. But last one is the membrane bioreactor, that our talk topic is. So if you use the membrane bioreactor, see the cost is around 5 times more than the conventional activated sludge processes. So cost wise, still it is not that much beneficial technique. And in between there is a combination. We are not going to talk that much, but third one is a CAS and the MFUF membrane. There is not membrane bioreactor, only membrane they are using, and those cost is increasing. Important, in membrane bioreactor, you get very high quality of the water product, and even you can reuse. That is one of the advantage. So if you have a water scarcity, there is no water available, then you input more money, more energy, but you get reuse kind of the water. Now, when we say, okay, compared to this slide says conventional process and the membrane, cost is high. But if you look at, because membrane bioreactor technology commenced in 1990, first time they have started in the laboratory in 1990. And if you see 1999 to the 2006 graph only, Here and the energy consumption, you can see drastically energy consumption is reduced in membrane bioreactor, and that what I call is a mature technology. That means in membrane bioreactor, the energy consumption definitely reduces with the time. And the sharp cost decline of the membrane for the membrane bioreactor. Another slide that only talks about the membrane, because again, membrane is the heart of the membrane bioreactor technology. And uh, if you reduce the membrane cost, that means your technology, the membrane bioreactor overall process cost also drastically reduced. That means continuous effort has been put forward to reduce this kind of the cost. Okay, so yeah, this is the example only the membrane from the xenon actually. So yeah, it is, they have taken that particular kind of the supplier. Now this is the real membrane bioreactor. This is configuration. So now I explain you what is the bioreactor. So you can see on the left is the bioreactor. When I say bioreactor is the same thing, you put some organic food, that is a wastewater. Wastewater have some organics. You have bacteria already in the system. Now if you refer the previous technique, you have no membrane. In this, you have a aeration tank and clarifier. That means overflow from the tank goes to the clarifier. You have to give enough time in the clarifier in terms of 1 day, 48 hours also. Then only the things will settle, solid will settle, and you recycle back to the system, and then you discharge part of them. What you can see here is now bioreactor is connected with the membrane. There are two ways. One is the whatever the supernatant from the bioreactor, it goes through the membrane, or the membrane itself you have put in the bioreactor tank. So first system is called side stream and second one is called submerge. Side stream means it is aside, the bioreactor and the membrane are separated, but whatever come from the bioreactor, instead of going to secondary clarifier, it goes through the membrane. So there is no need of the secondary clarifier. In the submerged system, you in whole membrane you put in the system. So you can see compared to the aeration tank in the previous slide I showed conventional process and the secondary clarifier. Secondary clarifier is very big in the diameter and it consumes lot more space in actual treatment plant. So if you put your membrane in the system itself in the same bioreactor tank, that means there is no need of the secondary clarifier, and that called reducing the footprint. That means the space requirement in the plant is reduced a lot. That is one of the advantage. Another bigger advantage is that when you use the secondary clarifier, whatever effort you do, but you lose some of the biomass. But here 100% retention, technically 100% retention of the biomass is possible because membrane is a barrier. It only allows the water and some dissolved thing to go through. It doesn't allow the bacteria to pass through. And how, we will see in few more slides. So you can see here side stream module has a high cross flow velocity. So what basically you need to do, if you see the figure A, that is a side stream one, underneath the bioreactor there is a pump and then it goes to the membrane. So you are pumping the whatever the water, wastewater through this bioreactor to the membrane, and you see the out is the product, and then whatever does not pass through the membrane, it goes back to the bioreactor. So it is in the circulation. And to maintain this, you have a high cross flow velocity and that generate the turbulence. And because of that turbulence, you can understand that it does not allow any cake formation on the membrane surface. If cake formation take place, it is called fouling of the membrane. Fouling of the membrane is nothing but deposition of the solid particle into the pore of the membrane. As I said, membrane is the porous material, but very thin pores, very thin kind of the holes inside that in terms of the nanometer size sometimes or micrometer size. So only water mostly pass through, other things settle on that. But because of that resistance, water flow rate decreases, and that what we call fouling. One stage is there is no water flow, no permeate. So this out thing, in presence of the fouling, you do not have any permeate or the product out. So what is the advantage of the side stream system is because of this high pumping, the cross flow velocity you maintain, turbulence is created, you can understand, and then all the suspended solid goes back to the bioreactor. So you have a good kind of the permeate, that is flux is high. Opposite to that, submerged module, no feed pumping, so less energy consumption. Now here you have a pump in the side stream, but when you put your react the whole membrane module inside the system submerged, and then you take this thing out, that is through the vacuum. So there is no external pump like this high velocity pump. As a result, energy consumption is really low. But definitely it gives you more fouling because there is no cross flow velocity. So these are the configuration what you want to prefer. So if you go for side stream, you have advantage of the less fouling thing. If you go for the submerge, you have advantage of less energy consumption. So using submerged membrane module, conventional MBR system consume much less. How much? 1 kilowatt hour per meter cube versus 3 to 6 kilowatt hour per meter cube energy than that of the side stream. So if you go for the side stream, for meter cube of the water treatment, you consume 3 to the 6 kilowatt hour energy. In submerge, you have really less energy consumption. So these are the advantage, or what on what base you are making the choice, that is important. If your wastewater is really fouling propensity, you definitely go for the side stream. If it is normal kind of that, no more foulant or ordinary kind of the foulant, definitely you go for the submerged kind of the system. So these are the one more thing I miss here is whatever you do here in the submerged system, it's not shown here, but you have to blow the air. So you have the air in the bioreactor to survive the bacteria. The same air you use for the removal of the foulant from the membrane surface. But of course, that is called SOR, specific oxygen uptake rate. That is a minimum amount of the oxygen you need to supply in the bioreactor to sustain the bacteria. But when you talk about the foulant removal using the air, because if you forcefully input the air, fouling propensity definitely decreases in the submerged system as well. So the same air, but at higher flow rate, you use it to get rid of the foulant also. So that what they are talking about here. In side stream, aeration cost is low, around 20%, because you input the air only for the bacterial survival. For the submerged membrane system, aeration cost is high, 90%, because on top of that air, you have to input more amount of the air, more flow of the air to reduce the fouling propensity. High pumping cost, as we discussed in terms of energy also, that you have to pump more in side stream, but in here submerge you need not to do much, just you use the suction pump. Small footprint and the higher flux, lower flux and the large footprint. Large footprint is bit okay, just consider the higher flux, here it is lower flux, that correct. More frequent cleaning is required, that's definitely there, and the less frequent cleaning is required. Higher operating cost and the lower capital cost, here lower capital cost and higher, already I discussed more or less the point, so it's okay. Now this already we started talking about the membrane bioreactor, but I haven't talked about the membrane. Just I said membrane is a plastic material, plastic sheet, it has some pores inside that. So this is some of the thing about the membrane. If you can see the right hand side image, this vertical thing is the membrane, and you can see some small pores are there inside. On the left hand side, that is a combination of the thing, that is a wastewater. If you see the right hand side product, it is like a H2O. So two hydrogens are in the red and the oxygen in the middle. So only it allows the water to pass through. So this is one arrow that is inside and this is outlet side. So what it means that out of all these contaminant in the wastewater, selectively the membrane allows only the water molecule to pass through. So why? Because if you see the first line now, membrane is a thin layer. Yes, it is thin layer of semi-permeable material. So it is semi-permeable material. It has some small, very small holes that is used for solute separation as a transmembrane pressure is applied across the membrane. Now you need to understand it is kind of a resistance to the flow. If there is no membrane, there is no resistance as such. So to get rid of that resistance, you have to push the liquid through that. That what we call transmembrane pressure. That means here you have some upstream pressure, here some downstream. That is the delta P to get rid of the resistance. That is transmembrane pressure. What are the desired quality of the membrane? So it should have high selectivity. Selectivity means only it allows the water to pass through. High permeability, not only it allows the water to pass through, water flow rate should be very high. That means in 1 hour I need 100 liter probably. If it gives 50 liter, that called less permeability as per my requirement. So permeability should be high. Stability, mechanical, chemical, and the thermal stability. So membrane should be robust basically. It should not react with any of the contaminant that is present in the wastewater. And again, when I use the word selectivity, so degree of the selectivity is depend on the membrane charge and the porosity. So how porous the membrane is, and always on the membrane surface there is negatively charged most of the time, because it repels and attracts certain things. So for water application, your membrane should be normally negatively charged. So by combination of this thing, membrane charge and the porosity, we try to define our selectivity. So what kind of the material you are after, accordingly you try to make your membrane. So you fabricate membrane as per your desire. That is called selectivity. Okay, membrane with the symmetric pore are more uniform, while the asymmetric pores have variable pore diameter. So that is also the kind of fabrication or design thing. You want to make the uniform size of the pore all around the membrane, but when you fabricate the membrane using different techniques, it is not always possible that you get the uniform size. So that is they define symmetric and asymmetric. And intermediate phase that separates two phases from each other and set a different resistance to the transport. A separating layer that retains the larger molecule or the particle and allows the smaller molecule and solvent to pass through. So whatever the larger molecule of in the wastewater, then the pore size of the membrane, definitely they are going to retain. It did not go pass through. It remains in the this left hand side of the membrane, that means in the feed, and whatever you get as a product, that is something, it is smaller the pore size of the membrane and it passes through. Okay, now very briefly I take the how the membrane, like different kind of the membranes. So you see asymmetric membrane and the symmetric membrane. First I talk about the symmetric membrane. If you see in the bottom left hand side, that is the symmetric membrane, porous sponge. So it looks symmetry. Whatever the part of the membrane you see, it very much looks the similar. So when you make the membrane, you produce like that. And if you see the porous cylinder, so the pore size are almost very much same in there. When we talk about the asymmetric membrane has the selective porous layer on the top and the support layer in the bottom. Now there are different way, but importantly the porous support layer has a 50 to 100 micrometer thickness. Mind well, this is not the pore size, this is thickness of the membrane. And the selective top layer is a 1 micrometer thickness only, similar in here. So these are the asymmetric membrane, because it is not looks like uniform, but if you see in the cross section, this bottom layer and the top layer. So the top layer is a selective porous layer and underneath is the porous support layer. Here also dense top layer. So this is porous, that is it has a more pore on the left hand side, but when it is a dense mean it is not that much permeable, it is more like impermeable membrane. So this kind of dense top layer membrane are used in the gas based separation technique like per evaporation or some different. This selective porous membrane, and one more is here, very left right hand side bottom, the name is thin film composite, that is called TFC membrane. So again it is a 1 micrometer is the selective. Here not it is a like a dense top layer or porous top layer. It is a selective coating layer. That means you have a bottom support layer, kind of one membrane itself, and on top of that very fine layer, that is 1 micrometer, you try to impinge on that top, that is using the coating technique, that is called thin film composite membrane. So TFC and PA, polyamide thin film composite membrane, normally used in the reverse osmosis and the forward osmosis kind of the application. This one asymmetric but dense top layer, that is used in the nanofiltration application. Normally symmetric membrane in the left bottom is used in the microfiltration application, and this one left hand side is a UF mainly. Nowadays they start using another word is a UF, loose and tight kind of the membrane, but basically it is more like this, how your porous top layer or dense top layer works. Accordingly they use the word tight or the loose kind of the membrane, but more or the less it is same technique. So now these produce with different fabrication technique. Why I try to discuss this is because in forward osmosis, when I will talk about osmotic membrane bioreactor, we will mainly talk about thin film composite TFC polyamide membrane, that is more used in the that kind of the application, forward osmosis and the osmotic membrane bioreactor application. Okay, so now I am coming to these membranes now. So you see the right hand side image, microfiltration, ultrafiltration, nanofiltration, and not UO, but it is RO, reverse osmosis. And if you see the wastewater matrix on the left hand side, and particle size here greater than zero point 0.2 micrometer, macromolecule, that is MW is the molecular weight cutoff, that is the 2 kd to 500 kd, that is kilodalton, and here 200 to 2 kd, then ions and the solvent. So what it shows here is microfiltration membrane, it allows the even larger side of the things to pass through, that you can see the red dot. Then UF membrane, it has kind of some colloidal and the bigger impurity, still it passes through that. If you see the nanofiltration, only divalent ion from that water, only divalent ion, rest of everything stops, it rejects. And in the reverse osmosis, only small monovalent ion and the solvent pass through. So this is how the membrane, all different kind of the membrane works because of the pore size. And these pore size dimensions are written on right hand side. So if it is a larger pore, its rejection is less. It is very small, thin, fine pore, its rejection is high. So RO membrane has the pore size in terms of the nanometer, and as a result, its rejection is maximum. It almost rejects everything. It only allows the water to pass through. And we talk about this membrane previously. So TFC membrane, thin film composite membrane, porous layer is little larger, but on the top skin layer, the coating layer is very small. Technically, it is impermeable membrane. They call semi-permeable sometimes, but so that is the reason you get this kind of the separation. So porous membrane used for microfiltration and ultrafiltration. Non-porous, basically it is semi-permeable, but they use the word non-porous. That is for the nanofiltration and the reverse osmosis kind of the application, even in the gas separation. And this figure in the bottom is nothing but the cross flow velocity. So feed, it goes to the parallel to the membrane, and whatever the reject, that is called returnate or concentrate, and whatever the pass through the membrane is the permeate or the product. So that how membrane gives the separation. So again the same thing I try to explain in one more. So this is the raw water, and here permeate is the desired product. If you pass through different microfiltration, ultrafiltration, nanofiltration, or the RO membrane, to push the thing through the membrane, you have to apply some pressure, because if the pore size is small, very small in terms of in case of the reverse osmosis, you can see 0.001 to the 0.0001 micron, that is nanometer actually size. So you have to push the water very hard, 10 to the 150 bar pressure you have to apply. That means your pumping cost is very high, but you get very high purity product, almost water. And that's the reason we use RO in our domestic use also. In case of the microfiltration, the transmembrane pressure or the pressure requirement is less, 0.2 to the 5 bar. And these all different kind of the impurities you can see on left hand side, everything is there in the water. But as you use one by one different membrane, MF followed by UF followed by NF and RO, finally after RO you get very pure water. After NF you get divalent kind of the monovalent kind of the thing. After UF you still get something like submolecular organic groups and the divalent ions and all that. So how membrane separation, but you can see very easily in the first like even in the MF, bacteria is totally retained, because bacteria is like zero 0.4 micron and your membrane is around 0.1 micron in the MF microfiltration. So whatever the membrane you use, basically it retains the bacteria. So these are some of the applications. If you refer to the only last kind of the row, in what kind of the application it is. So I wrote colloidal bacteria in the MF, pharmaceutical, that is a UF, retention of the dye, definitely nanofiltration, and importantly desalination of brackish and the seawater. So now we have a water scarcity. If all the source of the water is exhausted, we have the water in the sea 96%, as I say 96.5%. So you have to use the seawater, and using the reverse osmosis membrane you get the potable water. Already people have started doing it in Middle East country and many more other countries, and we are not far in India even, I believe. So reverse osmosis is that technique. So it gives you salty water to the potable water, because it has capacity to retain everything. So it removes all kind of the ions. Okay, now comes the membrane module. So how membrane looks and how actually it is not like only a small piece that I was talking of plastic sheet, but when you have to treat a huge amount of the water, you have to make kind of the cell, kind of the big module. So there are four basic kind of the membrane configuration, membrane module configuration: plate and frame, spiral wound, tubular, and the hollow fiber. And area to the volume ratio is one of the important. Mainly plate and frame and hollow fiber are more popular. Spiral wound is also there in some applications, but you see here area to the volume ratio is very high. That means it provide very high surface area, and cost comparison is also there, and some of the advantages. So you see compact design. Hollow fiber has a compact design actually. And how it looks. So hollow fiber membrane looks like this. So actually in industry or the treatment, this kind of the membrane. And Kubota is the name of the supplier, Huber is the name of the supplier. This is right hand side bottom is the tubular module. So this is the plate and frame module. So hollow fiber, plate and frame, tubular. I'm not sure about this, but yeah. So these are the membrane modules. And this is again hollow fiber membrane module used in the laboratory. So what it is, if you see the one fiber, this white fiber, it is in the U shape. If you don't attach to this thing on the plastic, it is a fine wire kind of the filament. But this is deliberately torn in the U shape. And on the left hand side, you can see all these openings you can see here. So basically what we do, the U-shape part sits into the water, and then on the top where you can see on the left hand side, the spores are there. So you connect your pump there with the tubing, and you try to withdraw the fluid from there. So it is called outer to inner kind of the mechanism. That means whatever the water is attached to these outer fibers, water selectively go into the bore of the fiber, that is called lumen actually, and then from the top you can collect using the peristatic kind of the pump or the vacuum pump. So how it works in laboratory practice is like this. Now when we talk about the membrane bioreactor, there are some of the major consideration. So fouling and the fouling control, that is one of the important thing. Then organic matter removal, that what we call is the food in terms of BOD and the COD. Nutrient removal, that is nitrogen and the phosphorus. So till now what I spoke, I didn't include the nutrient removal, but as we know, if you in the wastewater or any kind of the water, if you throw to the aquatic water body or the land, what happens is because of the excessive nitrogen and the phosphorus in the water, it leads to the eutrophication. That is the phenomena, and it is not good thing because entire water body get polluted. It is called algal bloom because of the unnecessary high amount of the nutrient like nitrogen and the phosphorus. Unnecessary growth of the plant happens, and because of that unnecessary growth of the plant, if it is in the water body like a lake, it keep taking the oxygen. As a result, for other microbials or the other aquatic life including the fish, there is no water availability, no oxygen availability, and as a result they die. So it is not, eutrophication is not desired phenomena. So it happens because of the excessive nitrogen in the phosphorus. Mainly it comes from our household application like detergents or sometimes fertilizers people use in the farms. So we need to get rid of the nitrogen in the phosphorus also. So membrane bioreactor is also used for that. Trace organic compounds, so all the pharmaceutical, that means the medicines we take, some of the hormones we use in the daily life, perfumes and kind of fire extinguisher we use, all have some trace organic compound, and that is in terms of the microgram per liter to nanogram per liter limit, not milligram per liter even, but they are very dangerous because they are persistent micropollutant, very hard to remove from the water matrix. So membrane bioreactor is also used for that application. That is the major consideration. Mixing and the hydrodynamic, we already talk about the shear velocity, turbulence, and then it mitigate the fouling. Sludge production, characterization, and the treatment. We only talk about sludge, that sludge produces in the end, but what is the characteristic of the sludge, what kind of the treatment is required, and the oxygen transfer. So as I said, minimum amount of the oxygen is required for bacteria to grow. So if I talk about this activated sludge process or membrane bioreactor, it is like a 2 to 3 milligram per liter is the ideal value. Of course, it changes. You have to actually calculate it mathematically. That called SOUR, specific oxygen uptake rate. But this is the normal range. If you input that, still bacteria can survive in the system. So you have to continuously give the oxygen. If deplete oxygen is no more there, then bacteria can't survive and then your process can't work. This is the concentration polarization. It has also some significance with the fouling, but I don't take it because we have many more other things to discuss. So factor influencing the fouling in the membrane bioreactor. So again, I briefly mention about the fouling. What is fouling in the membrane bioreactor? So membrane is the heart of the process and it has a small pores. If any of the particles from the water body, suspended particle, dissolved particle, colloidal thing, or even the microorganism sits on the membrane surface or goes into the membrane pore, and then because of that there is no water flow, that selectively water has to pass through the membrane, but because of this retardation, because of this resistance of this particle that settles stick on the membrane surface, it is called cake layer formation or gel layer formation. There are different words to describe it, or the pore blocking phenomena. This kind of the phenomena is known as a fouling, and because of that fouled membrane, no water can permeate through. Basically, you have to stop the process in that case. And some of the fouling is like a reversible fouling. So using some cleaning technique, you can get rid of, you can remove the foulant, and again you can put the membrane in the practice. It works again in normal way. If it is a irreversible kind of the fouling, there is no remedy. That means your membrane is now out of order. You have to replace with another membrane. That means it has extra cost. So fouling is very important, and there are some factors that contribute towards the fouling. So first is membrane itself. So what is the configuration of the membrane? Just now I talk about that module, all that. What kind of the material membrane is made of? what is the hydrophobicity or hydrophilicity of the membrane, what is the porosity of the membrane, what is the pore size of the membrane. So these are some of the membrane relevant property. Then come biomass. Biomass means bacteria, and normally biomass is expressed technically as a MLSS. That what we call mixed liquor suspended solid. So mixed liquor suspended solid is a total suspended solid. We can define it like a TSS, total suspended solid in the system. And another word is a MLVSS. MLVSS is the mixed liquor volatile suspended solid. So mixed liquor suspended solid is a combination of, you can say, live and the died bacteria, because after some time bacteria dies but still it remain in the system and it is in the solid form. So it is like a, or we call it a mixed liquor. Mixed liquor means the combination of the water and the solid. So this mixed liquor, and what are the suspended part in there, is called mixed liquor suspended solid, and out of which what is the live part, we call it mixed liquor volatile suspended solid. Another is a very frequently used term is a EPS, extracellular polymeric substances, and with another relevant another terminology is called SMP, soluble microbial product. So EPS and SMP are nothing but EPS are like a kind of the macromolecule protein, polysaccharide, kind of another nucleic acid. So all that makes the EPS, and mainly it is surrounded around the bacterial skin, that means outside of the bacteria. And the soluble microbial product is something coming from the bacteria when the cell lysis happen. That means if bacteria break, when bacteria break on unnecessary high temperature or any shock load, or the shock in the food load, that means you are feeding the bacteria at certain flow rate, certain kind of the food, all of the sudden if you change something, then bacteria can't survive and it secretes the enzyme or whatever the body fluid from there, and it is soluble form, so it called soluble microbial product. Now it is kind of biology thing also there, but EPS and the SMP are more studied thing nowadays because it has a maximum fouling propensity, so that are a contributor to the fouling, and therefore people study a lot. And if you take the EPS or SMP, again they try to divide them bound and the unbound, and again in bound and the unbound mainly they talk about the polysaccharide and the protein. So polysaccharide is mainly sugar. So polysaccharide and the protein analysis is also there. It is entirely different kind of the techniques. But when you read any this kind of the literature papers for defining the fouling to the membrane, they describe always how much EPS, how much polysaccharide, how much protein is there, and accordingly they write, oh, this is the more, that means more fouling propensity kind of the thing. Then come flock structure. Flock is the microorganism are like it clog with each other. It always try to retain in a group, and that makes a flow. And then, especially in the activated sludge process, when it goes to the clarifier, you have to give some time, and then it slowly settle down. So that called flock formation and the settlement. So if the flock size is good, then only settling is possible. So if your system is not good, that means flock formation is not good, and then as a result that they measure the flock diameter and whole flock distribution. So what is the minimum size and what is the maximum size, and then there is always a Gaussian curve. So that is the distribution of the flock in the system. So from that they try to define that whether the sludge characteristic is good or not based on the flock diameter. So both this flock size and the flock structure already I talk about, again the same thing in there, how the flock is formed, that is very important. And operating condition, we are not going much detail in there now. CFV, cross flow velocity, already I talked in the side stream membrane. Air, how much air you have to supply. In air, again there is a coarse bubble kind of the aeration and the fine bubble kind of the aeration. So if you supply the big kind of the bubble, what happens? If it is a very fine, if it is fine, surface area is higher and it has a more chance to mix with the liquid and more uptake by the bacteria. So it is good in one way. But if you try to generate the fine bubble using the orifice, very small thing, more compression cost is involved. So that is always trade-off. Another is a HRT and SRT. As I said, when we talk about operating condition, hydraulic retention time and the sludge retention time would be there. Now, very simple. If you're in the reactor, from one side you input and another side you take it out. So how long your water molecule remains in the system, that is called hydraulic retention time. Similarly, from the clarifier, activated sludge, recycle activated sludge goes to the aeration tank, that is bacteria basically. So how long bacteria stays in the system, that is your sludge retention time. And it is very simple. If you keep longer HRT, water molecule has, that means the food has more time to remain in the reactor. As a result, bacteria can eat easily and more degradation is possible. That means the quality of water improves a lot because degradation happens. Similarly, if you have a longer SRT, long time the bacteria retains in the reactor, so it acclimatize. That means whatever the environment in the reactor, whatever the different kind of the food variety, it used to with that. As a result, degradation is good, more easily it can degrade. So longer SRT actually required where it is a trace organic compound or the microorganic that is called persistent micropollutants are there. You have to acclimatize, you have to give the bacteria a long time to stay in the system, then it gives good degradation. So these all are related parameters. And transmembrane pressure, as I said, it is always there. Uh, uh, Based on the membrane even, that if you have an MF or the RO, the transmembrane pressure varies. Okay. Now we already talk about the fouling. What is fouling? What are the contributor of the fouling or the affecting thing to the fouling? So in short, fouling is not good. If fouling happens, you have to do frequently the backwashing or stop the membrane operation or change the membrane. So it is not good from process point of view. It interrupts the process. It includes the more energy. It includes the more labor and the cost of the membrane itself. So what to do then? If fouling happens, there are some anti-fouling strategies. So first one is the air-induced cross flow, then intermittent permeation, membrane backwashing, air backwashing, and then some chemicals also used. So air induced mean you use the air, that already we discussed. Intermittent permeation. Intermittent mean what? If you are withdrawing the liquid, as a result on the membrane surface, the particles or the solid try to attach. Now, instead of continuously taking the permeate, that means the outlet product, if you stop in between, so whatever the thing attached to the membrane, it try to loosen because there is no flow, there is no movement, you are not withdrawing the liquid deliberately. That means the whatever the thing attached to the membrane, it try to loosen and fall back to the reactor. So that is called intermittent permeation. Membrane backwashing. Backwashing means what? From one side you use the vacuum or suction and remove the product, that is a pure water, but as a result on the outer side of the membrane fouling happens. When you say membrane backwashing, mean from the same permeate, part of the permeate you backflush. That means in the opposite direction you try to push the liquid. As a result, whatever the thing attach on the outer surface of the membrane, it detach, and that called removal of the foulants. And the air backwashing, instead of the permeate, you can use the air or any gas in the same way. So it try to forcefully come out from the membrane into the out. As a result, whatever attached to the membrane, it detach. And these are like anti-fouling. These strategies are during the operation. When the operation is continuous, you can use all of them without physically removing the membrane out of the system. But when you use the chemical, sometimes chemical is okay, you use the daily or weekly or once or twice a year, that is an intensive chemical cleaning. So I show you that part here. These are left hand side is the supplier of the membrane, Mitsubishi, Xenon, Memcor and Kubota, and in the bottom I have written the Japanese manufacturer like Kubota, Toray, it's spelling mistake, TORAY, ASI and the Mitsubishi Rayon. In North America, there is a GE and the Koch membrane. So worldwide, this kind of the membrane are very famous. These are the name of the supplier at present also. So now these are membrane manufacturer, and when they give you the membrane module, they recommend some recipe. They tell you that if you use this kind of the chemical with this concentration and protocol, then your fouling is reduced. You can use your membrane more continuously in operation. So they recommend CIL, that is called cleaning in line, and CIP is the cleaning in place. So there are two different kind of the cleaning strategies. And when say cleaning in line, that is when the membrane is itself in the system, you input some chemical to remove the foulant, because this chemical actually attack on the foulant layer, and foulant are mainly the organic and the biological, that is the microbes. So when, for example, chlorine, you see NaOCl, sodium hypochlorite, so basically it is a chlorine, and chlorine is a disinfectant agent. So whatever the thing attached to the membrane, it try to kill the bacteria if it is living, and then it detach from the surface. So that is cleaning in line. But when cleaning in place, it is called vigorous kind of the if your fouling is very high, you have to actually stop the operation, take out the membrane from the tank, and then you practice this kind of the thing. So sodium hypochlorite is mainly used for the organic and the biological kind of the thing. If it is inorganic, then you use the citric acid. And what are the concentration? This already recommended by them, because they practice in their laboratory first in pilot plant, and then they suggest. And then protocol, backflow through the membrane and shocking. You have to keep shock the membrane in the chemical for 2 hours, and then you backflow for 2 hours. Then your membrane is again ready to work. So these are some of the technique how you do the cleaning. Okay. Now I think I am already taking a time. 7:58. Barad Sahib. Hello.
Yes, sir.
Is it
Yes,
okay?
yes.
Time point of view, it is okay. Boring.
Now we can conclude.
Conclude.
We can move towards the end. Okay.
Okay.
But I think forward osmosis is pending, I think.
Okay. Okay. I do it. I understand what you say. Okay. So what I do here is I take very quick study of the membrane bioreactor for the textile wastewater, and then I move to the osmotic membrane bioreactor and conclude. So this is actually research work on the membrane bioreactor. Now, whatever I was discussing here, everything will come in play here. So very quickly, what I did during my master's is I use the membrane bioreactor for the textile wastewater treatment. That is the industrial wastewater treatment. And for that, I collected the sludge from the common effluent treatment plant Sachin. And then this is the characteristic, how much MLSS in the sludge, that is 6.25 gram is the live one, 11 gram per liter is the, then I acclimatize the sludge. And what I try to do is, I use two different kind of the dyes. One is the red dye, another is the blue dye, and therefore I keep that color. And these are some of the Cass number and molecular weight of the dye. And you understand, dye is the divalent kind of the thing. It only passes through the NF membrane, that means reject by the NF membrane. So in the membrane bioreactor, this is the membrane I use. That is the ultrafiltration kind of the hollow fiber membrane. It is made of the PES, polyether sulfone. That's what we call symmetric kind of the membrane, and modified PES, and test on the bovine serum albumin. Bovine serum albumin is kind of the foulant. So they test already membrane on that. That is, membrane is giving good rejection. And these are the dimension of the membrane. Important property is the total surface area of the membrane, 0.043 meter square. And its manufacturer is the Aqua Plus Water Purifier, Pune. Now, this is the schematic of the membrane bioreactor. You can see it, left hand is the feed tank. This is the pump. The liquid goes into the membrane. Mixing is there. And this U shape is actual UF membrane module. From that, the permeate comes using this pump. It goes to the final permeate collection tank, and in between there are some controllers and the pH measurement, conductivity measurement. This on the right hand side of the tank is the sampling pot and everything. How it looks actually, this is the reactor. Left hand side is that permeate tank, right hand side is the feed tank with the mixture and everything, and in this tank, middle tank, membrane is sit inside, and underneath you can see red is the blower for air. This is the middle tank that contains the membrane, and this is the membrane that I showed previously also. This membrane put in the system. Now these
So
are
there are
the,
some questions from the students.
yes please.
Hello.
Yes, I take up.
One question is that, yeah, okay. Sir, for wastewater treatment, ASP sludge is being recycling to manufacture mixed fertilizer depending on characteristics of sludge. What about MBR waste?
Okay.
I repeat the
Uh,
question.
okay, so that's the reason I keep explaining the thing. SRT, sludge retention time. And if you see that in membrane bioreactor, even technically, you can operate the system at infinite SRT. So that means infinite SRT means that there is no sludge wastage. That means whatever the sludge retain in the reactor itself. So if you have a no sludge, that means there is no issue, there is no point to uh, discharge the sludge or handle the sludge. That is one of the things, because normally what we do from that activated sludge process, either as he said, it goes some agriculture mixed with the fertilizer, whatever you want to do. Another thing is you have to keep in the sludge drying dead, and then naturally also under the sun, water part evaporate, and then that compacted sludge you have to send to the landfill site. Now that is some of the caution here when they say they can use the activated sludge to some fertilizer manufacturer or whatever the product manufacturing. You have to be very careful, because whatever in the wastewater, it also stays in the sludge more or less, because especially activated sludge process, there is nothing like a membrane. So as I said, nowadays last 10-15 years they are talking about the emerging micropollutant or persistent micropollutant, and it is even in the nanogram per liter. It is very dangerous. So if all these things are found in the sludge, and if you use for that kind of the application, somehow it is there in the loop. And I don't know if it used for the fertilizer, again you grow the plants from that, and then it again enters into that cycle, food cycle somewhere. But of course, yeah, you have the application. But for membrane bioreactor, uh, whatever the way you use the sludge in ASP, though it is a less quantity, less handling and less cost, but you can use in the similar application. Because when we talk about the flow size of the sludge and characteristic of the sludge, it is more or the less remain the sludge in case of membrane bioreactor. So technically both sludge are the same, and you can use for the similar kind of application as well.
Thank you, Parak sir. Well, another question from final year student: which substrate in aerosol tank? Which substrate in aerosol tank is used?
Yeah, so that is technical word. Substract is nothing. It is a wastewater. So basically what you want to do, you want to purify the wastewater, and you are using the bacteria as one of the media. So they will eat up whatever the wrong thing in the wastewater and grow. And after bacteria become grow and more populated, we have enough, because our volume of the tank is fixed. That means how much amount of wastewater in the tank at particular time, that is also going to be fixed. So you need 100 kind of the 100 bacterial population, and at certain growth, remaining you discharge. That what I call is the recycle activated sludge. So from clarifier, 70% you recycle back, 30%, this is continuous process, mind well. So 30% you continuously discharge, 70% you circulate. So substrate is nothing, but that is a food for the bacteria. For us, it is waste. So wastewater is the substrate in this case.
Okay, thank you, sir.
Does it make sense?
Yes, yes,
Okay.
yes, it makes sense.
Should I continue or what you suggest?
Yeah, yeah, yes, continue, sir.
Okay, okay. So
Continue.
now I take very quickly now. So I am happy because this kind of the question mean because if you don't understand a basic process, then MBR and other things are like it's nothing there. So this is good actually. Question means at least reaching message is reaching there. That's good.
There is
Okay, so yeah, operational parameter of the MBR system with dispersed rate die. As I said, I used two different die. Now, this is the test on the hydraulic retention time, HRT again. So 24-hour HRT mean it is very long time and 8.4-hour HRT is less time. That means the whatever the wastewater retain only 8.4 hour in the reactor compared to 24 hour. And then I operated 24, 18, 14, 11 and 8.4 hour. And volume. MLSS, you can see. So everything keep changing and accordingly hydraulic retention time, FM ratio, that is food to the microorganism ratio and other parameter keep changing. This is for the dispersed blue dye. And now we are going to discuss the result. In short, what we want to do is, if you change the HRT in the system, you can see 24 hour, 18, 14 and 8.4 on the graph. And I operated for 7 days, 7 continuous days at one particular HRT, hydraulic retention time. And what we try to do is pollutant removal in the membrane bioreactor, that is COD. So if you operate at different hydraulic retention time, the COD in blue is the inlet COD and the red is the outlet COD. And then this shows how much percentage removal is possible. So you can see with different HRT, almost it is 90% removal. So in between 8.4 to the 24-hour HRT, COD removal is it apparent that at 24 hour HRT it is really high, but you can't afford to give the 3 times longer retention time when the process is slow to get almost similar kind of the removal. So we try to optimize the parameter. Similarly, the BOD, that is biochemical oxygen demand, and at different hydraulic retention time, and you can see how much removal is there. And most important thing, how I miss here, there should be a color removal also, because dye is the color material, and I try to measure the color value also using the spectrophotometer. So I conclude here. So except at 8.4 hour HRT, more than 90% COD and the BOD removal was obtained at all different HRT. And you can see here on the first, taking the 35 day of the experiment as a whole, COD removal of 95, 93, 93, 91, 80 at all different HRT. So if this is the scenario, you can from that conclude that what could be your optimum HRT. This is the table. First one is a present study. You can see I use the UF 50 kilo Dalton of the membrane for the textile wastewater treatment for removal of the dye, 92.33% COD removal, 93.69% BOD removal in present study. And then I try to, these are the reference number actually. All the other people have done somewhere in different places on all over the world, what kind of the membrane they have used and what kind of the removal they have achieved. But we can see our data also are quite competitive. That means the treatment is good, and this is the thing we have taken from our local Sachin plant, CETP plant sludge. So that kind of the sludge is good to treat the textile wastewater. And UF membrane is good. Now if you compare here, see UF membrane, organic matter, dissolved organic matter, especially dye, has a very small 5,500 to 5,000 Dalton kind of the diameter, and your membrane is actually bigger than that. Though UF membrane was capable, because if you consider dye, you need the NF membrane, nanofilter membrane. But why UF membrane is also successful? Because sludge layer, biofilm, which get accumulated in the mixed liquor of the submerged membrane bioreactor, that achieve the further biodegradation. So we are talking about the fouling. In one way, fouling is bad, but when there is a kind of a foulant layer, though you can have a water flow, if you go for the continuous cleaning. So what happens, because of that extra additional layer, dye particle can't go through that, it retain in the system, and as a result biodegradation is possible. So that what how the system works actually. uh, this is experimented different sludge retention time. Previously I saw different varying the hydraulic retention time, now varying the sludge retention time. So I operated at different sludge retention time, and you can see same COD on the top, how much was the concentration and how it reduces with time, and what is the removal efficiency. Similarly for the BOD. So here also I conclude, because already we are running time probably. So an average BOD removal 87, 90, 95% at 15, 30, 45 and 60 day sludge retention time was achieved respectively. Now these 15, 30, 45 and 60 day SRT makes sense. Why I select that SRT? Because I showed previously what could be the range of the sludge retention time and hydraulic retention time in activated sludge process and in the membrane bioreactor. Here I want to point out one more thing. In the activated sludge process, HRT, that is hydraulic retention time, and sludge retention time are coupled. That means they are combined. You can't decouple them. But in the membrane bioreactor, because of the membrane, you totally reject the suspended solid, that means sludge, that means SRT, and only the hydraulic retention time you can vary, but sludge retention time you can decouple from the hydraulic retention time. That means only you allow the water to flow through the system, but because of the membrane you retain all the bacteria, all the microorganism. That what we describe as a sludge retention time. And if your bacteria retain in the system for longer time, then your biodegradation is always better. So 15, 30, 45 and 60, obviously 60-day SRT is very good, because you keep bacteria, once it enter into the reactor, it stays about 60 days actually. That means it gives more biodegradation. Now the thing is, why it is coupled in the activated sludge process? There is no barrier, there is no membrane. So whatever the overflow from that reactor, you want only water to pass through, and it goes in the clarifier. But with that, whether you like or dislike, definitely bacteria, microorganism, whatever the that solid part also goes, and then you have deliberately settled into the clarifier, and then you recycle back to the system. And in doing whole process, whether you like or dislike, you lose some of the acclimatized bacteria. That means it affects your biodegradation performance. That is the beauty of the membrane bioreactor. Your sludge is very acclimatized, it is very seasoned kind of the bacteria. As a result, it has capacity to even degrade the persistent micropollutant, or the basically we call it a very hard, that is refractory kind of the material, that kind of the compound, and dye is one of there as well, that they can get rid of this kind of the compound. Okay, so these are basically what I mean to say here is, and then we compare the result with the other study, and it says, okay, we are also having the favorable result. So this is color removal, and at different wavelength, both of the dye were measured in the spectrophotometer. Okay, now these are the data for that. So color removal, actually this is okay in both HRT and the SRT. And in short, membrane bioreactor can remove color 91.36%. In this table on the top, it is written in the present study. So if you see the activated sludge process, even see some of the MFHF kind of the membrane, only 58.7% of the color removal. But in this study, it is more than 90% color removal. And actually, I am not showing here. I have taken the photo initial and the final, and totally color has disappeared. So that membrane bioreactor. But if you take the activated sludge process, color removal is almost impossible. Hardly you can remove 10 to the 20% of the color from the system. So that is something. And these all are the parameter conclusion. Okay, now the same figure, the one I showed you before, but the bottom line is important. Hybrid FO can be employed. That means till now we were talking of MF or UF kind of the membrane. Remember, in membrane bioreactor, we never use the nanofiltration or the RO kind of the membrane, especially in the submerged configuration. MF still use sometime in the side stream, very less. But here we are talking of the FO, and technically RO and FO membrane are same. Only we in RO we push at very high pressure, that is called reverse osmosis. In the forward osmosis, there is no pressure, no hydraulic pressure. It happens because of the osmotic pressure. So, uh, Barad Sahib, one more time, continue.
Forward, give some
I'm
glimpse
moving to
about
osmotic.
forward osmosis.
Already I'm there. I just ask you, continue.
Okay, continue and conclude.
Okay. So, okay, this is the principle of the forward osmosis. So, you see the left-hand side is a feed, in between is the forward osmosis membrane, and this is the draw solution. Now, draw solution is something that it has, draw solution is normally we use the sodium NaCl, sodium chloride. So it has high salt, and the feed is the wastewater. So this is very saline solution. Feed water is a very diluted solution. There is no external force. Only the thing is the osmotic pressure. So draw solution is a concentrated, feed is a dilute. So natural phenomena is that from the dilute to the concentrated, automatically liquid moves. So this in between is the forward osmosis membrane. It only allow the water from the feed side to pass through. It mix with the draw solution. As a result, it try to dilute the draw solution. But what we are doing here is, because of the membrane, only water passes through the membrane. So when we say feed is a wastewater, so from wastewater, only pure water mix with this draw solution because of the osmotic pressure difference, that is concentration gradient. Because it has a high concentration, the feed has a low concentration, and therefore dilute to the concentrated, it tries to move. So what will happen, for example, I have 70 gram per liter of the sodium chloride, and if this process happens, because continuously draw solution circulate outside this membrane surface, and continuously the water from the feed mix with the draw solution, as a result draw solution become dilute. Now, my interest is not to have anything with the draw solution or wastewater. I am interested in getting the pure water because it is reuse application. I want to use the pure water somewhere. So now diluted draw solution, I somehow try to concentrate. Very simple. If you heat it up, that is basic distillation, you get the vapor, you condense it. So again, your draw solution is retained. That means you again can be used in the process, and you use the water, but distillation is again very high intensity process. So what they do is, once the draw solution dilutes, they use another membrane, that is mostly NF or the RO membrane. They push the draw solution through the membrane, they get the pure water as a product, and the draw solution again concentrate is used again into the system. So this is how the forward osmosis works. So it is a natural driving force, as I said. Several advantage. What are the advantage? High
So the forward osmosis is in most of the cases in combination with MF or RO.
always. I show that very quickly, because if
Okay.
this fundamental is little bit, then it will you can understand probably. I don't know about others. Okay, so low energy requirement. Why low energy requirement? Because if you see MF or UF, you always has a pump. Hydraulic pressure you apply, but here there is no pressure, it is only osmotic pressure. Whatever the chemical potential in the draw solution, we exploit as a property, and as a result we try to dilute the draw solution. So that's the low energy requirement. And reduce fouling potential. If there is no hydraulic pressure, you're not pushing anything, so there is no fouling propensity as such, or very reversible fouling you can say. But there are some of the drawback also. There is no ideal draw solution, number one. Most important thing is a reverse salt transport. We are happy that that only water coming through the these and draw solution become dilute, and we can have a pure water as a product in the end. But remember, reverse salt transfer from the draw solution, this is membrane is semi permeable, so whatever you do, but some amount of the salt travels back, that is called reverse salt transport or reverse salt diffusion. As a result, the after some time salinity increases in the feed side, and that is not good, because if it is a bioreactor, you have a microbes or the bacteria, and because of this thing, bacteria, they can't survive, because cell lysis immediately happens if the salinity increases. So that is one of the major drawback of the system. Another thing is the less flux, because after some time the draw solution become diluted, that means automatically the delta C value, driving force, decreases. As a result, flux automatically decreases. So normally what happen, because of they use the RO membrane, they do not have the FO membrane yet. So the same RO membrane, the TFC or the CTA, cellulose triacetate, or the thin film composite polyamide membrane they use. And because of that, in the FO, the support layer is very porous and the thick. So already flux value is low because of they call internal concentration polarization effect. So flux maximum you can start like 8 or the 10 LMH, and within 24 hours it goes down to the 1 LMH. That is one of the biggest issue with the forward osmosis and osmotic membrane bioreactor. So now I'm coming to, this is the principle of forward osmosis. Now when I put the FO membrane in the bioreactor, so you can see now wastewater, FO membrane, rest of the thing is very much similar like the membrane bioreactor. Only we are using FO membrane instead of the UF or MF membrane. These are some of the publications, Scopus data and all that. You can see on the right hand side now, that is a reconcentration unit. That means dilute draw solution, the first membrane is FO. Now outside, whatever come from the FO as a dilute draw solution, you pass through the another reconcentration unit, could be anything, membrane distillation, reverse osmosis, NF, or whatever you want. But fine, you have to get the product, that is a purified water, and whatever the reconcentrated thing goes back to the FO. So it is continuous loop. It keeps the closed loop, you can say. It's circulating. And here, because it is a bioreactor, you have always aeration. So rest of the thing is very much same, but you have a FO membrane. But what happened because of the reverse salt flux, after some time, whole reactor becomes saline because continuous reverse salt flux.
This combination is interesting.
Yeah, I show some of the more thing now. See, these are the, what are the remedies now? That is more important. We are not giving up here, oh, salinity is high, flux is less. These are some of the problems we know. Salinity buildup is there. Low sludge retention time. So low sludge retention time in what? If you operated low sludge retention time, not that less like the activated sludge process, but compared to MBR, definitely you are not operated infinite or 80-day or 100-day. 15-day or 30-day. So you can like frequently bleed the sludge from the system. When you bleed the sludge from the system, salinity also decreases in the system. So that is one of the thing you can do. Another thing is a development of the new salt mixture, inorganic salt with the surfactant. So they call myceli. You better understand myceli formation, and because of that, it forms kind of the layer on the membrane surface, and from the draw solution side to the feed side, it retards the flow of the salt. And that how we try to reduce the reverse salt transport. And most importantly, and that what we normally do, is the incorporation of the MF or the UF membrane to alleviate the salinity buildup. That means already you have a FO membrane. Now you another membrane you introduce into the same reactor, either it is a MF or the UF. And MF has a high flux, and you operate MF intermittently, continuously. You can design it as per your wish, and then you continuously take out the product, one product from the FO, another from the MF or the UF. But in MF and the UF, you get rid of the salinity. So continuously you withdraw, that means salinity in the feed side of the reactor decreases. As a result, overall salinity in the reactor is less, microorganism can at least survive. They have done some values. If your salinity in the reactor is 5 gram per the liter, then bacteria can't survive. They start dying definitely at 8 gram per liter, that data says. So somehow you try to manage that value using whatever kind of the operation, MF, UF operation, intermittent, continuously, and reduce the salinity. And one more thing, when your reactor has a higher salinity, already your draw solution diluted. That means delta C is a minimum. That as a result, flux is less. Now what you do using MFUF from the feed side, you are taking out the salinity. That means your reactor become more diluted compared to before. And now you have a draw solution there. So delta C again maintained. So when you use the MF or UF, you can at least maintain the constant flux. It doesn't like fall all of the sudden, steeply reduce of the flux doesn't happen when you have that MF or UF kind of the membrane. So that is something. Already I discussed these things. So this is actual reactor. So how they work now. So this is the feed reservoir. FO membrane is there in the reactor. This is draw solution reservoir and the RO unit. You can see the RO unit. So now from draw solution, this blue line from the top goes into the membrane, FO membrane. And from other side of the membrane, it comes and it goes to the pump. So it is a closed loop draw solution. And after draw solution reservoir has that kind of the triangle, that is the level controller. So from that, we try to maintain the level, and this high pressure pump, because it is RO, you have to use high pressure pump. From draw solution reservoir, you input into the RO. So purified water you get from the RO. When I say purified water, definitely it is a potable kind of the water, you can say. And then from RO, whatever the concentrated, so you make up this thing, draw solution reservoir. And this is the feed reservoir on the balance. So how they measure the flux? Because you have the level control. So the because of the delta C, the FO take up the water, and that much amount
So
water
it
goes
seems
in
it is a
there. So
better
this
use of RO reject.
sorry.
I-
Again, please ask. What is your question?
RO reject is being used as draw solution.
Yeah, it is actually reconcentration of the draw solution. Because what happens, 70 gram per liter, for example, I use the sodium chloride, right? And
So it's
it
a
dilutes.
better reuse of RO reject.
It is not better reuse of RO reject. Deliberately, you are using RO as a reconcentrator because RO operating
Okay.
cost is very high. So FO is a energy, like a energy consumption. If you only go for the FO compared to an MBR, it is FO MBR is a less energy intensive. But there is no choice. You have
Okay.
to clock RO. So FO plus RO is energy intensive now.
Okay.
So what you can do, there is
Okay.
another remedy. So you remove RO, and draw solution you use once through. Once through, that means you need not to reconcentrate. Continuously you supply, and whatever the dilute, you throw it out. You are not doing anything. And you can do, if you use the seawater, for example, seawater has 35 gram per liter salinity. So if you use the seawater and you circulate, and after dilution you bring back to the sea, that's fine. Or whatever.
Okay.
Another thing is RO itself. In desalination plant, what they do, 35 gram per liter seawater they take. Even you operated 50% of the recovery. So after 50%, your concentrate becomes 70 gram per liter. So that 70 gram per liter is an issue where you throw it. So you use in the FO. After dilution, you can bring back to the sea. And they have a data that if you throw the high concentrated kind of the concentrate into the seawater, what happened with the marine species, but they can survive. It is not big deal. You have to at least use some high vertex zone of the sea. So that all thing is possible. So this is concept. Now this is the same thing. What I was showing there, aeration and bioreactor. One. This is side stream and the submerge that you understand easily now. This is important. That what I was telling you. You see dilute mode characteristic. So here no regeneration unit. You see the bottom figure FO membrane unit is there, and then RO brine or fertilizer. That is interesting to you because if you have a fertilizer solution you use in this reactor, so after getting the water, fertilizer become diluted, and that diluted fertilizer directly you can use in your field in the farm. That is one of the advantage. So when you do irrigation, you have to make the concentration of the fertilizer draw solution such that you know your system. And after FO unit, whatever the dilution happens to your fertilizer draw solution, it diluted draw solution directly you spread to the farm. So there is no reconcent unit is required. Or as I said, RO brine. RO brine is like 70 gram per liter. After the dilution, you send it to it is like a once through operation. There is no reconcentration or regeneration. And this kind of the dilutive OMBR is actually advantageous. So that I wrote in the last. RO brine 70 gram per liter or fertilizer can be used draw solution. And this is one of the real application. I quickly show you and then I finish. So this is municipal wastewater left hand side. And this is, forget about baffled world, OMBR and MF system. So FO is there. The square one is the, like a rectangle one is the FO unit. And right hand side is another MF unit. And what we try to do here is diluted brine for the safe discharge, and whatever you get from the UF, it is not the quality like the FO or the RO, but still that MF effluent after, because MF is mainly for the salinity reduction to alleviate the salinity in the reactor. That's why we use the MF membrane. But that MF outlet, it you can use as a green wall irrigation also. So that kind of the application, reuse application you can use. So your aim is there to bring down the salinity, but at the same time, you can use the permeate of the MF. And see how it works. The incorporation of the MF membrane was effective to maintain the salinity level. This range, 1.4 gram per liter is maximum. I told you 5 gram per liter is the danger, 8 gram per liter bacteria can't survive at all. But by continuous operation of the MF, salinity in the reactor you can control like this. It commences from 612 and maximum it reach 1434. This is the data for 30 days operation. And initial flux was 11.48. Because of the MF membrane incorporation, it reduced but up to 7 liter per LMH, liter meter square per hour. So that is very good actually, incorporation of the MF membrane into the system. So yeah, I spoke more on the fundamental thing, and I knew that actually, because now once someone understand all this concept, they can easily look upon the things. And what I suggest is this fertilizer draw solution, that means any kind of the fertilizer in concentrated form, and if you use the FO kind of the thing, diluted thing directly, you can use in the farm. In that way, it is helpful. Forward osmosis membrane bioreactor. So yeah, that's all from the presentation. If more questions, I am happy to take.
So thank you very much, Pathak sir. Is there any question from student side? Still you can ask in comment section. So once again, thank you very much, Pathak sir. It was a very much informative session. Good to know is that Dr. Neeraj Chawda also joined the session, and he has also written that it is an informative session.
Yeah, I understand,
so
and I
might have got so many.
Yeah, sorry to interview it. I made it informative. I knew that more fun, but when you deal with the undergraduate kind of the student, we can't emphasize on the research part because there are so many things involved. So that should be entirely a different thing. If that little bit a different thing actually, because it everything without any interest, they kept listening is.
चावड़ा साहेब પણ જોઈન કર્યું છે સર.
હા બોલો સાહેબ.
ચાવડા સાહેબ પણ સાંભળતા હતા.
मैं सांभळ्યું.
हाँ.
So is it now still recorded or off the record now?
Yes.